Hi, I'm Dane Quinn from the University of Akron, and today's video lecture will deal with coordinates. So, dynamics describes the configuration of a system of objects and how that configuration changes in time as a result of externally applied forces and moments, and in addition, of course, concerns with the initial conditions of that system as well. So, the configuration, in particular, is the location in space of all of the different material points that make up the object. So when we say configuration and location in space, really what we're talking about are the position vectors associated with each material point. So the configuration is defined in terms of position vectors of points. So the question is, what is necessary to describe position? So here in the figure, I have 2 points. I have a point O and I have a point P. So we'll let O be sort of the reference point, and we are interested in the position of the point P. Now P can move along this path as indicated by this curve. So the position vector from O to P will change in time. Right, so let's go ahead and construct and draw that position vector. So we'll label this as R of P with respect to O. And again, that's the position of P with respect to O. And it's a function of time because this position vector changes as the point moves along the path. What do we need, again, to describe the position? Well, we need a couple of things. One of them is represented as a basis. And this is a set of reference directions, typically fixed in the ground, but sometimes we'll use other directions for this system. And the analogy here, in terms of, say, a map, would be north, south, east, and west. Right? Those are our reference directions. We've all agreed on what north means in south and east and west. So if I told you to walk northwest, you would know where to go, because you understand what north means, and you understand what west means, and you understand what northwest means. Because again, at some point, we have all agreed that north is in a specific direction, and south and east and west are as well. So north, south, east, and west are our reference directions for a map. So that's one element that's required for us to actually describe a position vector. Now, the second thing is not just a set of reference directions, but measurements, right? And we refer to these as coordinates. So coordinates represent measurable quantities, right? So again, things that we can measure. And examples of coordinates are, say, distance. We can measure distance. We can measure angles. So they're measurable quantities that are used to specify the configuration of the system. So again, where a system is at. Or in this case, where is the material point P with respect to O. Typically, coordinates describe components of a vector, say a position vector, in specified directions. Right? So I might determine the horizontal component of this vector RPO, or the vertical component of RPO. Right? So that would be one thing that we could measure. Also, coordinates can be used to specify directions with respect to a reference basis. So we might describe the orientation of the vector RPO with respect to maybe the horizontal axis. And typically those reference spaces are fixed in inertial space, or the ground. The remainder of this lecture will be devoted to describing some specific coordinate systems and corresponding directions that will be useful for talking about and measuring and specifying positions in two cases, and actually velocity in a third set of coordinates. Well, the first one we'll look at are Cartesian coordinates, and these are associated with René Descartes, who lived obviously a long time ago. And Descartes described position vectors in terms of directions fixed in the ground. So here, for example, horizontal may be vertical, that might be I and J. Not necessarily horizontal and vertical, but certainly fixed in the reference frame associated with the ground. Right? So sort of this plane of the paper or the computer screen or whatever you're viewing this on, we could identify directions I and J like so. So here I is horizontal and J is vertical. Then we want to make measurements of this vector in those directions. So, for example, in the horizontal direction, in the I direction, we might determine that the component is x. Right? So again, that's the measurement that we make. In the vertical direction, we might measure the displacement as y. So then, the position, Rp with respect to O, is x in the I direction plus y in the j direction. Now, motion is associated with not just position, but velocity and acceleration. So let's go and calculate those two in terms of these Cartesian coordinates. So the velocity here is the derivative of position. And notice that although x changes as a function of time, as this point moves along the path, the I direction is fixed, right? Because I is fixed in the plane of the blackboard. So the velocity then becomes x dot in the I direction plus y dot in the j direction. Again, y can change, but j is fixed. The acceleration, likewise, is the derivative of velocity, or the second derivative of position. But again, similar arguments will provide us with the acceleration is x double dot in the I direction plus y double dot in the j direction. And dots, remember, are derivatives with respect to time. So x dot is the first derivative of x, dx dt. X double dot is the second derivative of x with respect to time. So now, for example, if acceleration is known, right, so let x double dot be some function of time. Right? And let's assume for a moment that y is identically equal to 0. Right? So this point P might only move along the horizontal plane. We can go from acceleration to velocity to position by integrating. So x double dot, and we'll use some dummy variable xi in place of time, is f of xi, and we want to integrate this with respect to time. Right, so I'll integrate from 0 to t d xi, and what does that give me? Well, this is the integral of a derivative. It's the derivative of x dot. So we get x dot at time t minus x dot times 0 is the integral from 0 to t of this function, f of xi d xi. So we're able to solve this for velocity. If I would like to go and solve for position, I'll do the same thing. Here, let's use a dummy variable tau. X dot of tau is x dot at time 0, again solving for x dot here, plus the integral from 0 to tau f of xi d xi. And once again, we'll integrate with respect to time. Integral from 0 to t d tau. So that provides the position. X of t minus x of 0 is x dot at time 0 of t, that's the integral of this term from 0 to t, plus, now we have a double integral, 0 to t, and then 0 to tau, f of xi, our dummy variable, d xi d tau. So in this example, right, if the acceleration was known, I am able to find, by integration, the velocity of the point and the position of the point. The next set of coordinates that we'll look at are polar coordinates. So now the position vector is described in terms of directions that move with the position vector itself. So these directions move with the position. Here, again, let's go and define I and j fixed in the ground. But then let's look at, say, a direction ER that is along the position vector and E theta that's perpendicular. And then we'll measure the angle theta between the horizontal and ER. And in addition, we will measure the length of this vector as a scalar, and we'll call it r. Remember, underbars represent vectors, and because this one doesn't have one, it is simply a scalar magnitude. And our coordinates are r and theta. So in terms of these coordinates, we can write the position vector as r of p with respect to O is some magnitude, r, in some direction, which in this case is ER. Now, unlike the previous example with Cartesian coordinates, the direction ER can change in time. So as this position vector moves around, as p moves around, ER changes with respect to the ground, as does the magnitude. So we need to understand, if we're going to look at the velocity and acceleration, how both the magnitude and the direction vary in time. Well, we've already dealt with that in a lecture on vector derivatives. Right? So here, the directions ER and E theta spin with respect to I and j with angular velocity that is given to us and measured in terms of theta dot. So the angular velocity omega of ER and E theta is simply theta dot in the k direction. Theta is the angle, so theta dot is the rate of change of this angle, or how fast this basis spins with respect to the ground. As a result, we find that dt of ER, so the derivative of ER, recall, is omega cross ER. Well, omega was theta dot k, and so k cross ER simply gives me e theta. And the change in ER, the derivative of ER with respect to the ground, is theta dot e theta. Looking at e theta, we have a similar result because the derivative of e theta is omega cross e theta. The angular velocity is theta dot k, and k cross e theta becomes minus ER. So the derivative of e theta is minus theta dot in the ER direction. Now, we have two sets of directions here. We have I and j, and then we have ER and e theta. So let's go and relate those two. So here I'll show ER and e theta. And then we have the directions I and j that are fixed in the ground. And the angle between I and ER is given by theta, again, up here. So we can relate ER and e theta to I and j by just doing a little bit of trig. Right? And we've covered this in a previous video lecture, so I'm just going to write this one down. ER is cosine of theta in the I direction, it's this distance, plus this distance, which is sine of theta in the j direction. E theta is minus sine in the I direction plus cosine in the j direction. So we've related ER and e theta to I and j, but we can also relate I and j back to ER and e theta. And we've done this in a previous lecture as well, so I will just kind of go through it quickly. I is cosine of theta in the ER direction minus sine of theta in the e theta direction, while j is equal to sine of theta ER plus cosine of theta e theta. So we're able to, again, relate these sets of directions to one another, and we're able to find how these polar directions, ER and e theta, vary in time. So now we're ready to go and write down the position, velocity, and acceleration. Well, the position we've already said, right? So the position was r of p with respect to O is r in the ER direction. But now let's look at the velocity. So the velocity of p is the derivative of the position. So when I take the derivative here, I get dr dt in the ER direction plus r times the derivative of ER. Well, the derivative of ER from the previous slide was simply theta dot e theta. So this becomes r dot in the ER direction plus r theta dot in the e theta direction. And for the acceleration, we will take the derivative of velocity. So the acceleration, d dt, of the velocity of p. So once again, we'll take the derivative of these terms. Right? So it's d dt of r dot in the ER direction plus r dot times d dt of ER plus the derivative of r theta dot, that's the magnitude, in the e theta direction plus r theta dot times the derivative of e theta. Well, when I work through this, the derivative of r dot is r double dot, and the derivative of ER is theta dot e theta. And so those I will go ahead and denote. Right, so this is theta dot e theta. We can work this out, and the derivative of theta dot is minus theta dot er. And so, as a result, when we work this out and collect terms in er and e theta, we have r double dot, right, from here. Now, this term is going to be minus r theta dot squared, because I have a theta dot here and 1 contributes from here. So that's in the er direction. In the e theta direction, this, notice that d dt of r theta dot is equal to r dot theta dot plus r theta double dot. So we have r theta double dot from here, and then we have an r dot theta dot. We also have a second one here, so we end up with 2 r dot theta dot in the e theta direction. So now we can identify these components as radial and transverse. Right? So the radial components are in the ER direction. Right? So these are the radial components of velocity and acceleration, while the transverse components are in the E theta direction. And these are just the names that we give to these two components. So we have the radial component of velocity, the transverse component of velocity, and then the radial and transverse components of acceleration. Now, I will note that the speed of this point is defined as the magnitude of velocity. Right? So v, and this is a scalar, is the magnitude of the velocity. Again, the velocity is a vector, but the magnitude is a scalar. So one simple way of representing that is to take the velocity and dot it with itself, and then take the square root. Because when I dot a vector with itself, I end up with the magnitude squared. In terms of Cartesian coordinates, let's go back and look at that. Velocity was x dot in the I direction plus y dot in the j direction. So the speed becomes the square root of x dot squared plus y dot squared. In terms of polar coordinates, right, when I do the same operation, I get r dot squared plus r theta dot squared. So we have two different expressions for the speed. They're entirely equivalent. We are measuring different things in each case. It's either the square root of x dot squared plus y dot squared, or it's the square root of r dot squared plus r theta dot quantity squared. Our previous two sets of coordinates were based on the position. Right? So we used the position to define, say, x and y, or r and theta. But we can also base coordinates on the velocity. And those are referred to as normal and tangential components. So the velocity here can be defined in the following way. If I look at the velocity, for example, it's going to be tangent to the path, and we'll call that Vp. So then Vp is v, which is the speed, in some specified direction, et. Et is going to be along the direction of velocity. And then we'll have a second direction that is directed inward along the path. So et is this direction, and en will be, again, the orthogonal or perpendicular direction directed inward to the path. So once again, the directions ET and EN move with the point. Right? So as the point changes and moves around, then ET and EN can move with it. So they move with the velocity. And here I won't derive this, but I am going to go ahead and state it. The acceleration is defined as A of P is V dot in the ET direction. So really what we're doing is taking derivative of the magnitude in the ET direction plus the magnitude times the derivative of ET, how ET changes in time. And it turns out that that becomes V squared over rho in the normal direction, where rho is defined as the radius of curvature. And this is something that must be calculated depending on the path. So if you know the path that the point follows, you can find the radius of curvature. And then EN, again, is directed inward toward the center of curvature. Right? So the center of curvature is going to be represented and denoted by a point C. So looking down here, we have the velocity that's tangent to the path. Then, geometrically, the center of curvature is located at the center of a circle that sort of best fits the path at this instant. Right? So if P is here, we can construct a circle that best fits that path, and the center of that circle is the center of curvature. So a couple of things to note, and this is the important one. For a circular path, it makes sense that a circle best fits a circular path. And so rho is identically equal to the radius of the path. Right? And again, that kind of makes sense. If the path can be written as some displacement in the y direction as a function of displacement in the x direction, right? So y of x is again some function. Then the radius of curvature is defined as it's this expression: 1 plus dy dx squared, and that whole thing to the 3/2 powers, and then in the denominator the second derivative of y with respect to x. Right, so this is the definition of the radius of curvature. More often than not, we'll use this in examples where the path is circular or the radius of curvature is given. So again, for circular paths, the radius of curvature is identically equal to the radius. So here we have a set of coordinates that are represented by v, the speed, and some angle that orients the tangent direction that's based on the velocity rather than the position. Again, this set of coordinates is most useful when the path is circular, so that the radius of curvature right here becomes constant. Well, what we've seen in this lecture are 3 sets of coordinates that can be useful to describe the configuration of the system. And throughout the course, we'll use all 3 for certain kinds of problems. So that's it. Thank you very much, and I will see you again.